Hi, welcome to the next lecture. This will deal with graphs of numerical data. So here we have a sample of birth weights in ounces, 103 ounces, 106 ounces, 48 ounces, 96 ounces, and so forth. And there's various types of graphs we can make. I'll start out with a stem plot, also called a stem and leaf plot. The first one or two digits is going to be the stem. The last digit will be the leaf. So our lowest birth weight is 48 ounces. So that's the lowest stem is going to be the 4. And our highest birth weight is 117 ounces. So our highest stem was going to be 11. And so the first thing we want to do is put these stems in order from smallest to largest. You could go below 4 if you want. But there's going to be no leaves that go in that row. But anyway, you go at least from 4 to 11. You can go a little bit past that if you want. And then once we have the stems in place, then we want to put in the leaves. So so the 103 ounce baby, the stem is 10 and the leaf is 3. So we want to put a 3 in row 10. That's the 103 ounce baby. The 3 in row 10 represents the 103 ounce baby. And then we have a 106 ounce baby. That would be a 6 in row 10. So this looks like 36, but the 6 really represents 103 ounces. The 3 represents 103 ounces. The 6 represents 106 ounces. And then we have a 48 ounce baby. That's going to be an 8 in row 4. Put an 8 here in row 4, and then 96, put a 6 in row 9, and then we have 110, that's a 0 in row 11, 98 is an 8 in row 9, 104 is a 4 in row 10, 85 is a 5 in row 8. 117, that's a 7 in row 11. 103, that's a 3 in row 10. Okay, so here's our stem plot. And that's more or less finished, except it's traditional to put the leaves in order from smallest to largest. So the only row where the leaves are out of order is row 10. The rest of it we can copy the way it is. We have 8 in row 4, 5 in row 8, 6 and 8 in row 9, and then row 10 we want to do smallest to largest, so we'll have 3, 3, 4, 6, and then row 11, 0, 7. So that's our stem plot. Just a comment here, for larger data sets, sometimes they split each row into 2 rows, and for example, in row 10, if we split this in 2 rows, we'd have the lower numbers in the first row 10, so leaves 0 through 4, that'd be 3, 3, and 4 would go in the first row 10, and leaf 6 would go in the second row 10. 6 through 9, 5 through 9 goes in the second row. So that's with the larger data sets. You might want to do a split stem plot. Okay, so then, so what does this tell us about the data? Here's our stem plot. What does this? Well, if you turn this sideways, usually you want to turn this sideways. And here I did this on the next page. Here I actually turned it sideways, we see the overall shape of the distribution. We have a big hump here, and then it kind of peters out. We have a long tail on the left. This is sometimes called skewed left, and this 48 ounce baby is pretty far from the other data, so that could be considered to be an outlier. So we have one main cluster, and it's skewed left with an outlier of 48 ounces just from the graph. There's more precise ways of determining outliers, but usually we'll just look at the graph and eyeball it. There's other shapes that you might have. Ours was skewed left. We have the longer tail on the left. It could be symmetric. The left side is the mirror image of the right side. It could be skewed right. The longer tail's on the right. you can have a uniform distribution where the birth weights are pretty much evenly spread out over that interval. Or you could have a bimodal distribution. Maybe you have one group of babies with low birth weights and a higher group of babies with higher birth weights. So those are some of the shapes that you can look for. But in this particular case, we have a skewed left distribution with outlier 48 ounces. Okay, so that's a stem plot, and that's one of several types of graphs we'll be working with. Another type of graph is a histogram. For a histogram, you first want to group the data because you don't want too much detail in the graph. Usually, sometimes if you have too much detail, it kind of obscures the forest for the trees. But anyway, so you're looking for overall patterns. So it's oftentimes helpful to group the data for histograms. So I group these by tens. We have one baby in the 40s, nobody in the 50s, 60s, 70s, and then we have one baby in the 80s, two in the 90s, four between 100 and 109, and two between 110 and 118. And then once we have grouped the data, then we can make the histogram, and we make a bar for each of these intervals. So 40 to 49, the frequency is 1. We have one baby there, so the bar goes up to 1 for 40 to 49. And then nobody in the 50s, 60s, 70s. 80 to 89, we also have one baby. The bar goes up to 1. And then 90 to 99, we have two babies, so the bar goes up to 2. And four babies, 100 to 109. The bar goes up to 4. And then two babies, 110 to 119. Okay, so that's our histogram, and pretty much it tells us the same thing as the other graph. It's skewed left, one main cluster skewed left. We have an outlier of 48 ounces, so that's pretty much the same. So so you don't really want to describe the graph specifically. You want to really say what the graph tells us about the data. So it's not so much the individual characteristics of the graph, but what the graph tells us about the data. And usually that's going to be the same whether it's a histogram or a stem plot. Some types of graphs we'll get into later. There's a type of graph called a box plot that we'll get into later that is very good at showing symmetry versus skewness, but does not do so well with other features of the graph. So, but generally, each type of graph will pretty much tell you the same thing about the data. Okay, so there's we were using frequency in our histogram. We were using the frequency as our vertical scale, and we could also use relative frequency. So if we did a histogram using relative frequency, you would divide the frequency by the total number of babies. From 40 to 49 ounces, our frequency is 1. We had one baby. The relative frequency was 1 divided by 10 because that was 1 out of 10 babies. You could also make it into percent. If you multiply by 100, percent means parts per 100. So if you multiply by 100, you can make that into a percent. 0.1 times 100 is 10%. And likewise, you can fit the other frequency. 50, 59 ounces, we had 0 babies. 0 divided by 10 is 0. Multiplied by 100, you get 0%. And 88, 89 ounces, again, we have 1 baby. 1 divided by 10 is 0.1. Multiplied by 100, it's a 10%. 90 to 99 ounces, we have 2 babies. 2/10. 2 divided by 10 is 0.2. And 100 to 109, we have 4 babies. 4 divided by 10 is 0.4. So these are the relative frequencies. Multiplied by 100, you get the percent. And it's basically the same graph. It's just the scale is different. Instead of going from 0 to 4, we're going from 0 to 0.4. Our highest bar is at 0.4. And this vertical scale here gives the relative frequency. If we do the percent, the highest percent here is 40%, but basically it's the same graph. And this description is still the same. It's skewed left with an outlier of in the 40s, and it's one main cluster. Okay. Okay. So the another type of graph is a dot plot. Dot plots are good for medium-sized data sets. They don't really. I don't like them so much for small data sets. But we can do a dot plot here. With medium-sized data sets, you can actually show the clusters better. Usually, with medium-sized data sets, you'll have more duplicates, and when you have duplicates, you kind of stack the dots, so you get more of a hump. A small data set, you just have sort of a string of dots. But anyway, we have a 48-ounce baby, so put a dot there for the 48-ounce baby, and 85 ounces, from 85 and 90, 96 and 98, 102 at 103. So then we can stack the dots. When you have duplicates, then you stack the dots. 104, 106, 110, and 117. So again, we have one main cluster here. It's in the 80s to, like from mid 80s to between 110 and 120. That's where most of the dots are, and then we have this one outlier. So again, it's skewed left with an outlier of 48 ounces. Another type of graph is a pie chart or a circle graph, and because there's 10 babies, I kind of divide the pie into 10 pieces. If I had 8 babies, I probably would have divided it into 8 pieces, but here I have 10 babies. So each baby is going to be a slice of the pie. So we have one baby in the 40s. So we can use the same grouping we used for the histogram. We have one baby in the 40s, nobody in the 50s, 60s, 70s, one baby in the 80s, 2 in the 90s, 4 between 100 and 109, 2 between 110 and 119. So these represent the number of slices of the pie. So we have one baby in the 40s, and that'll be one slice of the pie. Just one baby, 40 to 49 ounces. And then we have nobody in the 50s, 60s, 70s. We have one baby in the 80s. And we have 2 babies in the 90s, so that'll be 2 slices of the pie. 4 babies between 100 and 109. There's 4 places, 1, 2, 3, 4. And we have 2 babies between 110 and 119 ounces. So we have 2 slices there. 2 babies, 110 to 119 ounces. Okay, so that's our pie chart. And again, you could do percentages too. I just did the number of babies, but you could say 20%, 110 to 119, 10%, 40 to 49, and so forth. And that concludes this presentation.